In part 4 of this series, we'll explore examples where x approaches infinity. The question reads, find the limit of each function, and for a, we want the limit as x approaches infinity for the function 8 plus x over 4. To do problems where x approaches a non-number, for example infinity, you want to predict what will happen if you input a very large number into your x for the function. So if I inputted a really large number into x and divided it by 4, I would still end up with a pretty large number. And the greater x becomes, the larger that number becomes. And because there's this continuous increase in the size of the output, we say that for a, the limit is infinity. And this is also evident by the graph shown below. Notice that as x increases larger and larger, this continues to go up. In part B, we're asked to find the limit as x approaches infinity for the function 5 over x minus 3. Now once again, I want you to approach this problem by thinking of a very large number being placed in the denominator of this term. Dividing any number by a very large number, pretend it was 100 million, you'll end up with a very tiny number. And that tiny number is so small that it's negligible. It's not even worth mentioning. So pretend that you had a very small number minus 3. So our answer here is simply negative 3. And of course, I can prove that with our calculator. Let's say I had 5 divided by a very large number. I get 5 times 10 to the power of negative 11 minus 3. This gives me simply negative 3. In part C, we're asked to find the limit as x approaches infinity for the following function. Just like before, you can start by inputting a very large number into x. But if you do that, you'll notice very quickly that inputting large numbers into this expression won't help us find the limit. Take, for example, 4 times a million to the power of 3 minus 3 times a million to the power of 2. You don't really know what's happening. So to do this type of question, you need to use your math intuition. For instance, you need to use math techniques that will manipulate the function where you can find the limit. You can try factoring the top and the bottom, except the top, the numerator, is a cubic function, and cubic functions are generally hard to factor. So that's not helping. You can try to factor the bottom. That's probably more factorable given that there's an x in common, but it still won't help us since the numerator is a pure cubic. Another technique is to multiply the top and the bottom of this quotient by the reciprocal of the highest power. Take, for example, this expression. Notice that the highest power here is x to the power of 3. So what I can do is multiply the top and the bottom of this fraction by 1 over x to the power of 3. And what I do to the bottom, I need to do to the top. Now this technique is not used very often, but you have to do what works. And in this case, it will. If I multiply the numerator by 1 over x to the power of 3, I end up with 4x to the power of 3 over x to the power of 3 minus 3x squared over x to the power of 3. And I'm multiplying each of these terms by this fraction plus 5 over x to the power of 3. Similarly at the bottom, 3x over x to the power of 3 minus x squared over x to the power of 3 minus 5x to the power of 3 over x to the power of 3. What's evident now is that this x to the power of 3 and this one can cancel out, and so can these. X to the power of 2 can cancel out, and you end up with x at the bottom. This remains the way it is. This cancels out with one of these x's. Two of these x's cancel out with 2 at the bottom, leaving you with 1 over x minus 5. Now I will take the limit of each individual term, both in the numerator and in the denominator. And you can do that using the properties of limits. That's allowed. So this term remains 4. That doesn't change. Minus 3 over x. If I input a very large number into x, and we discussed this earlier in part A and part B, you end up with a very tiny number. In fact, so tiny it's negligible. It's unimportant. So this becomes 0 minus 0 plus the same condition as before, plus 0. 3 over a very large number is 0. Here we have 1 over x, so minus 0. 1 divided by a very large number. And finally, minus 5. So we end up with 4 over negative 5. I'm simplifying this expression. Therefore, the limit for this function is 4 over negative 5, and that's also evident by this graph shown below. Notice that as x gets larger and larger, the function, which is represented by this curve, starts to approach negative 4 over 5. And so there you have it. 3 examples on how to evaluate limits using algebra and the limit laws.